In this video, we're going to be introduced to electron configurations and learn how they are linked to the orbital diagrams we've already seen for multi-electron atoms. This is the orbital energy diagram for multi-electron atoms that we were introduced to in the previous two videos. This diagram can be used to generate an electron configuration for any atom or element, which is just a shorthand notation identifying the number of electrons in each subshell of an atom. And electron configurations become very useful for predicting chemical behavior of atoms and especially for predicting how one atom or element will chemically bond with another. The shorthand notation uses subshell designations such as 1s, 2s, 2p, 3d, etc. And they're combined with superscripts to identify the number of electrons in each subshell of an electron cloud. And what we see here is the electron configuration for the lithium atom, 1s2, 2s1. So let's see how we get this electron configuration for lithium. If we go to the orbital diagram for lithium, we see that there are 3 electrons in its electron cloud, and they are distributed in a particular way, with 2 electrons paired in the 1s subshell and the third electron residing in the 2s subshell. And this, as I said, results in an electron configuration written as 1s2, 2s1, where the 2 superscript represents the 2 electrons in the 1s subshell, and the 1 superscript represents the 1 electron in the 2s subshell. If we go to the next element, beryllium, atomic number Z equals 4, and therefore containing 4 electrons in its electron cloud, we can see that the orbital diagram is constructed by placing 2 of the 4 electrons in the lowest energy orbital with their spins paired, one pointing up, one pointing down. The remaining 2 electrons are then placed into the next lowest available orbital, the 2s orbital, also with their spins paired, one up and one down. The ground state configuration for beryllium is therefore going to be 1s2, 2s2, and we get that because there are 2 electrons paired in the 1s subshell, corresponding to the superscript of 2, which we therefore designate as 1s2. And there are also 2 electrons paired in the 2s subshell, which we designate as 2s2, again with the superscript representing the number of electrons in that particular subshell. If we now go to the next element, boron, atomic number 5 with 5 electrons in its electron cloud, we construct the orbital diagram by placing 2 electrons paired in the 1s subshell, 2 electrons paired in the 2s subshell, and the 5th electron then goes into the lowest available orbital, which is one of the orbitals in the 2p subshell. The electron configuration for boron is therefore 1s2, 2s2, 2p1. And we get that because there are 2 electrons paired in the 1s subshell, which we designate as 1s2, and there are also 2 electrons paired in the 2s subshell, which we designate 2s2. And there is 1 electron residing in the 2p subshell, which we designate as 2p1, giving the overall electron configuration as 1s2, 2s2, 2p1. And again, we note that the superscript in each case represents the number of electrons in each subshell of the electron cloud. Finally, we can further note that the total sum of all the superscripts in an electron configuration, in this case 2 plus 1, will be equal to the number of electrons in the electron cloud, in this case 5 for the neutral boron atom. In the next video, we will continue this approach to writing electron configurations by using the Aufbau principle and by following Hund's rule.